Right, good afternoon, and thank you for coming along to a few milliseconds in the life of an HTTP request. Today, every one of you expect web requests to serve you instantly. Who want to wait for page load times anyway, right? If your application or your website that you're accessing involved in page load time, what would you do? You go somewhere else. Regardless whether you're traveling, accessing the site from a poor mobile connection, or wherever you are in the world, you expect highly performant online experience. And the performance of your website or your application help you to convert from that anonymous user to a subscriber. I'm really passionate about the technology that helps to move packets in just a few milliseconds. My name is Chanka Pereira. I'm a solutions architect here in London, working predominantly with the customers with media, telco, and entertainment segment. I'm with AWS a little longer than 3 years now. But before joining AWS, I was a customer for good 5 years. I'm also part of the SME group, which is predominantly working with the Edge services and Edge platform portfolio. I'm here with Fabrizio Fortunato, head of front-end from Ryanair Labs, to share their story of migrating their applications to CloudFront and wider Edge portfolio. We will be available after the session outside this theater room to answer any questions that you may have. And also just a reminder that this is a 300-level session, so I would expect you to have some background in networking and got some understanding of our Edge portfolio already. So without further ado, let's get started. So let me start with a quick overview of the massive infrastructure behind CloudFront. Today, we have around 169 point of presence, which we call them POPs, worldwide. And each one of these POPs would be able to ingress hundreds of gigabits to a local ISPs and to Tier 1 carrier network. Majority of these POPs are using AWS backbone, a privately managed network which is provide our customers better resiliency and quality than the public internet. And today, CloudFront being used by millions of AWS customers and to host some of the largest events across the globe. I'm here talking about tens and millions of requests per second. And our Edge portfolio has been grown rapidly over the last few years. Last 12 months itself, we have added more than 40 to 50 point of presence to our platform. This is on top of upgrading the existing infrastructure. If you are interested about our global network infrastructure, I would recommend going to the infrastructure.aws, which has an interactive map showing you our regions, availability zones, point of presence, and the connectivity across them, and also talk to you about our future development and where we are going to launch next regions. So let's have a quick look at the request inside CloudFront. Imagine that you host a website called london.com, and that contains images. And you wanted to accelerate the delivery of these images. And let's have a look at how our Edge portfolio helps you to do that. So first, you create a CloudFront distribution, which generates a unique domain name ending with .cloudfront.net. Then you create a DNS record, which is pointed to your domain name that you created. In our case, we use Route 53. And I would recommend using alias record because it is a cheaper and faster way to resolve and allows to resolve Apex domain, which is in our case. So then, when the user resolves the london.com, the domain using the DNS resolver, query being handled by CloudFront DNS service and grab the IP address of the best server or the POP that would able to serve your request. Then the user established a TCP and TLS connection. which then makes an HTTP request and serve you the images. And this is the image that I've taken walk into a tower bridge, because I had to walk across Tower Bridge for a good 3 years every work day. And this is, I think, 5-6 years ago in December. So like myself, you taking pictures and you got pictures in your websites that you need to accelerate. Why not use CloudFront? Let's zoom into the first step, which is the DNS resolution segment. So actually, part of the DNS resolution, we have a big data problem to solve to deal with the scale of AWS operating net. Because we need to figure it out, what is the best server to serve user requests while optimizing performance and availability. And for a challenge, we need to do this in real time. Because if there's a congestion or a server failure, we need to route the traffic around and make it transparent to the end user to protect the customer experience. For that, we need to create feedback loops. We are doing this by ingesting information in real time from multiple sources and constantly updating the routing table and presenting back to CloudFront POPs. Every time a user requests a TCP connection, we capture and measure the round-trip time taken for that three-way handshake. We take this information and we process it through Kinesis Stream. We use Kinesis consumer library and we build a table of POP for latency to the user network. And using another system, we create a table of POP latency to a resolver. We measure the POP health using CloudWatch matrix. And we use the CloudWatch API to extract the information and put it into our control plane. And obviously, there are other things that we measure, like server capacity or network utilization. To dive deep about how we handle this, I would highly recommend you watch 2017 reInvent video, Measuring the Internet in Real Time, CDT 406. So now we make HTTP request to the selected POP. The amazing journey of HTTP request begins in CloudFront. Let's have a look at how it looks like. But before doing that, you may have probably heard during other sessions today, security is our job zero. Before using or sending any packets to CloudFront, we scrub it in layer 3 and layer 4 and look for DDoS attacks, using internal technology that we built to cope with the scale of AWS. We only allow traffic that is intended for CloudFront, which is 480 and 443, HTTP and HTTPS traffic. We also use SYN flood mitigation techniques and proxy all the incoming connections and verify them. We also look for suspicious activities during traffic shaping. We score traffic based on multiple dimensions and to understand whether it's legitimate traffic, whether it's a DDoS attack. For example, we look for abnormal sources or cache busting, and based on that, we prioritize our traffic while reducing the false positive. We call this built-in protection shield AWS Shield. And if your customers who needs access to all the DDoS attacks happening across the world, or need help or support from our DDoS response team, we would encourage them to sign up for Shield Advance. Let's go back to our CloudFront layers now. When the HTTP request lands on our POP router, after passing the DDoS mitigation, we will forward that into a random server in layer 1. This is the user-facing layer, which is responsible for making that TCP and TLS session with the users. And there's a small cache to deal with very high popular content which we need to get it back to the user quite instantly. If the content's not in layer 1 cache, we'll hash the URL, we accept the encoding headers and any other values that you've been forward part of your CloudFront distribution, and based on that hash value, we find the correct server from the layer 2. And again, if the content's not there in the layer 2 cache, we constantly hash the origin IP and based on that hash, we select it from layer 3. Layer 3 is responsible for maintaining that persistent connection to the origin, avoid new connections happening at every cache miss. But it also depends on the content type. As you well aware, your packet will be routed to most relevant layer based on your content type. If it's if the content need to be frequently served, and if it's popular, we keep it in layer 1, and we directly serve it from the layer 1 cache. If the content is not that popular, L1 identifies that it doesn't need to go to layer 1, and it's fetching from layer 2. And now, if you configured your CloudFront distribution as a proxy to forward for a dynamic content, forwarding all the headers in your CloudFront behavior, we even skip layer 2 and make a faster connection to layer 3. And actually, if the dynamic contents get very popular and frequently requested, we even skip layer 3, because we know the amount of traffic will keep the connection from layer 1 persistent to the origin. So idea behind this layering mechanism is to keep the open connection and reuse the open connections as much as possible, rather than making a new connection for every cache miss. We also have a regional edge caches. In our CloudFront global infrastructure, in Europe, we have regional edge caches here in London, as well as in Frankfurt. So instead of POP requesting dynamic content directly from the origin through layer 3, it will fetch from the regional edge cache. This is particularly useful for content that are not that popular, which we call them long-tail content. And we have 11 regional edge caches across the globe, and there's no charges for using regional edge caches. Let's dive deeper into the services provided by these layers. I assume that most of you are familiar with the TCP three-way handshake. So first, we establish a TCP connection, which is important for reliable communication. Then, we do a TLS session, which is important for confidentiality, authentication, and integrity. The challenge with these protocols are the latency that they cause, because TCP requires 1 round trip time for the three-way handshake, and then TLS requires 2 round trips for verification, cipher capabilities, and key exchange. So we already spend 3 round trips in total before we make an actual HTTP connection. CloudFront uses a protocol called TCP fast open and TLS resumption to send cookies, and it will contain the information that we already negotiated with the parameters for the connection. This way, when the next time the user comes to the same server, he or will send the cookies and establish a connection using a 1 round trip time. Of course, security is a shared responsibility. We are responsible for the infrastructure, and you are responsible for your application code. URL signing, field-level encryption, geo-blocking, HTTP to HTTPS redirections are some of the measurements that we have taken in layer 1 to improve that security posture. And then we got AWS WAF, the Web Application Firewall. A good web application firewall should be able to help you quickly set fundamental protections and customize your applications. Customers can simply enable roles in WAF and protect them against any kind of different kinds of application level attacks, like HTTP floods, cross-site scripting, SQL injections, to name a few. But what makes AWS WAF stands out as a service? Because it helps customers to innovate quickly and innovate fast. As majority of AWS services, AWS WAF has an API, and also changes propagate quite fast, less than a minute. So you can use these mechanisms and the features to build a feedback loops and automate security aspects using services like using the wider AWS ecosystem and services like AWS Lambda, Athena, CloudWatch, S3, to name a few. AWS Lambda is a serverless compute function which we can execute on per request based, and you only pay for the function execution time. So this is a solution that we have in our answers page, and it is being written as infrastructure as a code, and the Git repository being shared as well. So you can actually deploy this solution using a couple of clicks. But because the source code is already available and including the CloudFormation templates, you can customize that for your needs. It's mainly handled the OSAP top 10, but let's go through a few automation pieces that you have part of this solution. So the first one, it executes a Lambda function based on the CloudWatch event and take the IPs from open source lists and IP reputation lists and frequently update the IP reputation list to block the bad actors. The second one, when the logs getting landed from the WAF logs as well as CloudFront logs, and we use the Athena, which is the querying mechanism to the data that is landed on S3, and look for suspicious activities, look for rated 400 errors, look for anomalies, and based on that, we have built at automation processes to capture those source IPs and put them into a block list. And the third one is a honeypot that we created using AWS Lambda, an API gateway. And in robot.txt file, we asked the bots not to make a request for the honeypot, but the bad actors would do. And we'll capture it, and we'll block it. And all this kind of automation being built in around this solution means with a couple of clicks, you would be able to deploy it and enhance it and improve it as infrastructure as a code. Another service that would help you to help customers innovate fast is AWS Lambda at the Edge. Lambda at the Edge is an extension to a Lambda function which you can execute it closer to your viewer using while attaching to CloudFront requests and responses. Lambda at the Edge uses full programming language, Node.js, so you can do advanced things like making external network calls or using external libraries. Customers can trigger Lambda at the Edge functions in 4 different event triggers: viewer request, viewer response, origin request, and origin response. In the viewer events, we typically see customers implementing like custom authentication mechanisms, security solutions such as bot mitigations. Let's have a look at the caching layer, which is our layer 2. So the main goal of this layer is to improve the cache hit ratio. By increasing the cache hit ratio, you can serve requests faster to your users. Rather than traffic goes to origin, you can also reduce the origin capacity. I've already talked about how we leverage the consistent hashing to shard the content that placed in layer 2 and layer 3. And then I spoke about the regional edge caches, how it works as a CDN for CloudFront, and reduce the number of requests that's going back to the origin. And then we use a technology called response streaming. So when the object is not in the cache, we need to take that from the origin. But we will serve the request as soon as we receive from the origin. This technique reduces the latency for the first byte. And finally, we do request collapsing. This happens when the objects become very popular and suddenly everyone requesting for the same object. A good example is a big sporting events and when you try to watch it from a live web stream. So this is where the first user requests for the stream, and then you got another user requesting for the same stream. CloudFront collapse these 2 requests, go to the origin, get the response back, and once you get the response, it will send the response back to the both users. In fact, it's about how you set your cache control strategy. I would highly recommend that you spend a lot of time and looking at the architectures of your application stack and look at how you improve your cache control strategy. Because not all the contents are the same. Some are frequently get updated, some are not. Some are private content and some are shareable. Some might have variance than others don't. So you need to set your cache control strategy in a granular basis, and CloudFront allows you to do that. Let's take a simple example looking at an e-commerce website. For your HTML content, which is changed quite rapidly, you want to make sure all your users get the latest version. So you can do that using e-tag values and set minimum TTL values on a corresponding behavior. For the API, like your shopping bucket or baskets, you proxy all your proxy and forward all your headers, skips the caching layer. So you don't set caching for these items and take the request from the origin. But for your static contents, you will set the long TTL values, and you can use the URL versioning to update these contents. But what if you have to take the content from the origin after doing all that? So layer 3, we establish a connection to the origin, and we maintain a pool of persistent connection to the origin by reducing the overhead of establishing a new connection at every cache miss. This would avoid TCP slow starts for every new connection. In general, CloudFront is when the connection is established, CloudFront sends the request and wait for the configured origin response timeout values. And if the response is received, it would make retries before it fails. So initially, it will make 3 retries to establish a connection, and after that, it would wait for your timeout values that you've been set into your application and make another 2 retries before it fails. As a customer, you can configure these caching timeout values. So what happens if the origin fails? You can configure the origin statically for a specific CloudFront behavior. You can also select it dynamically using Lambda at the edge origin requests. In fact, in this layer, CloudFront triggers Lambda at the edge functions only when there's a cache miss. This is an opportunity to you to modify that. So basically, you can do things like, based on your cache miss, you can set some cookies, and based on the cookie values of your users, you can route the traffic that is best served for your customers. At this stage, you can also generate content dynamically without needing to have origin at all. Origin response events being triggered when you receive the response from the origin, and it is chance to modify that request before it caching in the CloudFront. And then we'll look at how we can gracefully fail over. As a customer, you can configure the origin failover using CloudFront to route the request to your backup origin upon failure. Please note that the failure happens after 3 retries from the main origin. And by default, if the origin request is failed, CloudFront will serve the stale content. Even if the cache is expired, it will still serve the stale content to avoid degrading user experience. And of course, if the content is not in the cache, CloudFront will send an error message, like the dogs of Amazon. But you can use, you can also configure the custom error pages, or route your traffic into a static page, or even use Lambda at the edge to build up a custom error handling logic. So that's it from me today. I will now invite Fabrizio to talk to you about flying in the cloud.
Hello, hello. Can everybody hear me? Yeah? Go, great. Okay, so just take that one, thank you. Okay, great. Hi everyone, so thanks Chanka and thanks AWS for having me here today. Let me introduce myself. My name is Fabrizio Fortunato. I'm head of front-end at Ryanair Labs, and Ryanair Lab is what we like to call a tech company with an airline attached. Now, this is my Twitter and GitHub handle, Easy Fortune, and there's also my blog where I generally blog about front-end and serverless stuff. Now, I've been working at Ryanair Labs for the past 4 years, and today I'm here to talk about the adoption that we had of the AWS services, specifically CloudFront and Lambda Edge. So I want to start by giving you a little bit of a context on how everything started, a brief history of our migration, basically. 2 years ago in Ryanair, there was the decision to jump into the cloud. So this is where we started moving services from our on-premise data center into the cloud, specifically starting first with new services, and then slowly also replacing the old one, right? So to just have an idea of how our website is operating, here's an overview of the on-premise website infrastructure. In our data centers, we will have different servers for the CMS and the Angular application or single page application, and then also different servers for the APIs as well. What I would like to be focusing on this talk is these CMS block, these CMS servers. And now we managed to split the single page application from the CMS and use it as any other API, so basically as a headless CMS. To understand why this separation was necessary, the two main advantages that we gained were responsibility and scalability. So first off, responsibility, that's because in Ryanair, there are different teams that actually look after CCMS and another team, my team, that look after the single page application. And so this way, actually, the front-end team can start be responsible for his own infrastructure. And scalability, because single-page application in general are just a collection of static assets, which can be easily cached through a CDN. So what we basically build is the foundation for a serverless website. And today I want to answer the following question for you. What, why, and how? So what is a serverless website? To put it simple, like I consider it a serverless website. Any website that doesn't run on a classical web servers, but rather uses all the wide ranges of AWS serverless services, such as CloudFront, to use it as CDN, to take advantage of the edge caching, to have a secure connection also for the origin. S3 also, to store the assets, your page asset, your single page application assets. And finally, Lambda Edge, where it basically sits in the middle. You can add your business logic between your edge and your origins, and it's acting as a glue between the two. But why we should look at a serverless website? Well, any front-end team, I would say, has very little knowledge on what it takes to manage a server. And to be honest, this is not part of the responsibility of a front-end developer. Front-end developers should be looking at how the user interact with the page rather than looking at how much CPU the server is using. So using serverless technologies, front-end developers themselves can be responsible for the whole infrastructure, since part of this complexity is offloaded to AWS. And now we're going to look at how to run a serverless website through a series of use cases and how we implement it in Ryanair. So the first one that I'm going to analyze is how to emulate a basic functionality of a web server. What I'm talking about is the ability to create rewrites and redirects between the user request and the actual resources. So if we take a closer look at the life of an HTTP request, what we notice in here is that we have a request that goes to ryanair.com/ie/en. It will go through CloudFront. CloudFront then will have an origin set up as an S3 in this case, and a behavior to forward the traffic from the CloudFront to S3, right? So what happened here is CloudFront will forward these URI/ie/en to the origin, to the S3. Now, in our case, we don't have a single page application per each language. We just rather have one that serves all the languages that we support. So what will happen is that CloudFront will request this file en in the folder /ie, and it's not going to be there. So this is where you can actually use a Lambda Edge, and specifically an origin request, so that when the request is going from CloudFront to the S3 origin, the Lambda will intercept it and rewrite it to the actual file that is needed for that request. So the request then will be returned to CloudFront and then to the user. And that's it. You basically have any rewrites similar to any other Apache or Nginx server. With the difference that this is completely serverless, and the great thing, it just takes 3 lines of code actually to implement it. You see, you can just take the request from CloudFront, rewrite the URI, change the URI, and return it. Now, while standard rewrites are good to start off, when the single-page applications start growing, it might become harder to maintain. The Renner website started growing in parallel with our offices. So we started in 2014 with the Dublin office, then 2016 in Wrocław, and finally in 2017 in Madrid. And a single-page application was actually becoming unmaintainable, especially with all these different teams in different locations. So this is why we started exploring the concept of micropages. What we call a micropage is an independent developed and deployed page on the website. It is loosely coupled with other pages, which means it only knows what is the previous page, what is the next page. And it is a single-page application per page still. And these allow us to reduce the technical depth surface of the overall application. And we apply a strict performance budget to monitor the page performance. Now, if we have a look at the micropage architecture, this architecture breaks down your website into individual pages, which are managed by different teams. Also, the pipelines for these pages are actually separated and managed by the team itself. The pages are then connected to each other via a router who is responsible to direct the request to the specific micropage. So in this way, we have actually a clear separation of the team and his own page and pipelines on the overall website. This concept architecture translates very easy actually in AWS. If you think about it, CloudFront can act as a router for your request. You can define the different behaviors, and this is where you want to start doing your routing. So if we follow one request, for example, in our website, CloudFront will act as a router. Then we will specify some behaviors per micropage, specifically 2 behaviors per each micropage. One, which is necessary to get back the index HTML, similar to what we've seen before, which is doing the rewrites. And the second behavior, which is just for returning the static assets of your single page application or of your page. Both the behaviors are actually connected to the same S3, and of course in different parts of these S3. And at the end, we're also using for the pipeline AWS code pipeline, which is populating the S3 based upon the latest changes that you have on your repository. And this setup is basically replicated per each micropage. What we notice is that the result of this architecture, especially on the first micropages that we released, is quite impressive. So if we take the flight select page, the previous version was actually having a data transfer of 1.1 megabyte. And the current version is that if you navigate to our website in mobile, you can actually see it as only 372 kilobytes of data transfer. So by reducing the overall size of the application and applying strict performance budget, we managed to reduce the size of the website of around 66%. So this size reduction is also connected to a strict diet that we are following for our micropages. And I can assure it works miracles. It is a diet based on Brotli. And Brotli, for who doesn't know, is a compression algorithm which performs better than gzip. It is also a good modern browser support, as you can see here, but not every browser supports it. So in order to be transparent for the application, we developed another function which takes care of serving broadly compressed file only to the browsers that supports it. So let's assume that the request is coming for a JavaScript file, in this case foo.js. Then in Cloudflare, we will define a behavior which, for any JavaScript file, so like this behavior, we will attach an origin request Lambda. And this Lambda is checking the accept encoding header from the browser and serve the correct file to the browser. So as you can see here, we're actually storing now two files, one for broadly, one for gzip. And if you have a quick look at the code, it also shows how simple it is. So we take the request and the headers. We check if broadly is an accepted encoding, and then we just append either broadly or gzip in our URI and return the request. With this simple Lambda deployed, not only is transparent for the application, but what we notice is an overall reduction up to 23% between a gzip compressed file and a broadly compressed file. If you think about it, you're making your website faster of overall, like 23%, just by adding few lines of code, basically. Now, oops, too much. All the teams working on Micropages are constantly releasing new features. And you have to face the fact that there's going to be problems. Bugs will arise, especially while developing new features on complex systems. To try to alleviate this issue, what we wanted to build the tools to let the team feel comfortable releasing to production as quickly as possible, and at the same time do not impact a huge number of users. So this is why we build canary deployment for web pages and micropages on AWS. So when a request is coming for a specific page, the origin request Lambda that we've seen before is not directly grabbing the index HTML, but rather calling an external service, in this case, LaunchDarkly. LaunchDarkly is a service which allows us to store feature flag, and you can, has a nice interface to configure these feature flags. Now, each feature flag can also have a percentage rollout attached to it, which is basically defining the weight and the number of users that you want these feature flag to be served. In the feature flag, we store the version of our page, and then once the LaunchDarkly request comes back, the Lambda takes care of grabbing the correct index HTML file that is stored. That's it. We just created, you see, canary deployment for a serverless website. But what we noticed, though, was that by adding these external calls, our Lambda Edge duration actually increased up to 500 milliseconds. This is when we started looking how to reduce this duration and how to improve the experience for our users, and also to reduce your bill, to be honest. And so we improved this solution rather than calling an external web server. We are calling a DynamoDB table, and this DynamoDB table stores the up-to-date, all the up-to-date feature flags from LaunchDarkly, is acting basically as a cache, as a relay. The changes that we did on LaunchDarkly was to add a webhook. In this webhook, there's listening an API gateway where a Lambda sits, which is writing all the updates on the DynamoDB. The rest of the application stays exactly the same. And with this change, we reduced the Lambda at the edge duration of 350 milliseconds. So we went from 500 to 150 milliseconds. And what we noticed also, the impact on the user, this is the P90 of page load for our users. It went from 3.5 to actually 3 seconds. That's 500 milliseconds improved experience for our users. While creating a serverless website on AWS, another important aspect that you need to take care of is security. In particular, while serving a web page, you'll need to implement a specific set of headers that helps you out increasing the security for your user. So this is a list of all generally the security users that you can implement. You're going from XSS protection that helps you out alleviating XSS, finally to content security policy, CSP at the end, which define your security policy for your page. Now, when you first starting creating a serverless website on AWS, the headers are not going to be there. And this can be exploited by malicious attackers. If you haven't seen it before, there's a website, security headers, which basically gives you a grade of your website. So how can you start from a very bad F grade and go to a A grade, still maintaining a serverless infrastructure? If you haven't figured it out, it involves another Lambda Edge. This time, though, it's not an origin request, it's rather a viewer response. So what we're looking to do is, before the response is actually going back to the user, inject the security headers. And if we have a sneak peek into the code, it reveals how it is to set it up. We take the response from CloudFront, basically it's the first line. We then check if the response actually is HTML page. We only need these headers on HTML pages. So we are checking the content type of the response, and then we append the headers and return the response. So while all the previous use cases were specific to a specific request and response for our infrastructure, what happened when a user selects Ryanair.com without having selected any language or country? Now, this is a map of all the different bases and routes where we operate in European and non-European cities. What this translates to is an extremely big combination of languages and countries that we support on our website. When a request is coming to Ryanair.com without any language or country selected, then we created a function that takes care of it. So inside CloudFront, there's a behavior, just with the slash, in which we attach a viewer request lambda, which is basically applying a role algorithm. This algorithm takes in consideration multiple things, and amongst them there's, for example, the accept language a request header from your browser, and also CloudFront viewer country, which is a header that CloudFront injects and contains the country of the request where it's coming from. So based upon these different parameters, we then redirect to a specific country and language path. And to create a redirect through Lambda Edge, you just need to specify a status code for the response, and then the location header in the object that you are returning. To close out, I would like to leave you with some takeaways from our journey and migration into AWS serverless services. First, considering that we are the busiest travel website in Europe with more than 1 billion visits per year, what you're seeing here is that it's possible to run a serverless website at a big scale. But what I will suggest is always to check the limits that you might have in your account and monitor those, so that you know if you're informed if there are any problems. Then I encourage everyone to actually take in consideration your team skills and the business requirements while building your infrastructure or architecture. Like, you shouldn't build an infrastructure or architecture just on a new technology just because it's cool. I mean, serverless, it is a cool technology, but we had some needs ourselves as well. And finally, you see now through Lambda Edge simple and flexible interface, you can really focus on delivering features to your users. Thank you. And now I'll give it back to Chanka that is going to wrap up. Thank you.
Yeah, thank you, Fabrizio. Right. Yeah, thank you very much for coming to our session today. And I hope you enjoy the rest of your afternoon. And most importantly, please complete the survey of our session because your feedback is important to us to improve the more sessions like this in future and the events and for the future events. Thank you.